Now it's time to model the data that we will be working with. In our application, we will be handling HTTP requests and returning HTTP responses. Let's see how we would represent an HTTP request first. Here, I have a simple HTTP request that we can use as a guide to see what we need to implement. We see that it starts with the method, followed by the path. It might contain some query string, but this is optional. It might be missing. Then this is followed by the protocol. And on the next line, we have the headers, and at the end, we have the body. In our simple implementation of a server, we would only focus on the first line here. That means that our parser for HTTP requests will ignore the headers and the body. We would only want to parse this first line. So how would our request look like if it has to store the date here? Let's figure out. We would need a struct for our request. So we create a new struct and we call it request. And we see that our request would need to hold the path. The path would probably be a string. We might revisit this later. It also needs to hold the query string. So it will hold the query string, which let's say is also a string. And it would also need to hold a method, which is, I think here the method can be get, post, put, delete, or something else. So let's also make the method a string for now. Okay, this is a pretty simple implementation of a request. Let's focus on the method first. It doesn't really make sense to store the method as a string because it can't just be any possible string. The method can be one of predefined HTTP methods. Here in the Mozilla website, we can see a list of all the valid HTTP methods, and we see get, post, put, and a bunch of others. So how would we represent this in our code? Right now, in this string, we can put anything that we would like. Luckily for us, Rust has a feature called enumerations or enums that was built to solve exactly this problem. Enums are special types which have a finite set of values. We call the possible values of an enum its variants. You might have heard of enums before. A lot of languages have enums as a feature, but they greatly differ in capabilities. Rust's enums are very similar to the algebraic data types in Haskell. Okay, let's see how we would create our method enum. To create a new enum, we use the enum keyword followed by the name that we would like. So method. And in the body of the enum, we can list all of the possible variants that it might have. So we have get, we have post, we have put, but instead of typing all of this, I've already copied all the possible variants of an enum, which are 9. So right now we have this type called method, and it can be one of these 9 variants. So it cannot be something else. So if we change our method here to be of type method, right now our request can only have a method that is one of these variants. In memory, the variants of an enum are represented by simple numbers. They start from 0 and are incremented for every next variant. So in our case, if our method is get, in memory we will just store a 0, or 1 for delete and 2 for post. Let's actually see that in action. Up here in our main function, we can define a couple of variables. So let's define a variable get, and to create a new enum, we use the name of the enum followed by double colon, and then we just put the variant that we would like. So we would like our get to be a get, and then let's have delete, which would be a method delete. Let's see what's next, post and put. Okay, so we can create post and put. Okay, this is how we would create an enum. Like we always have to create a concrete variant of this enum. Now let's open this up in the debugger and see exactly how this enum is represented in memory. So to do that, first we have to compile our code. We see that everything compiles just fine. And as we remember, when we run cargo build, it will put the binary in the target debug directory. So in here, we can see that we have our server. So let's open this in GDB. Okay. Let's try to list our code. So we want to put a breakpoint on line 7. So we put a breakpoint in main.rs line 7. Okay. Now, if we run this, we see that now we're at the point where all of our local variables have been defined. So if we check that, we see that our local variables are these enums, but the debugger is actually quite nice here, and it shows us exactly the variant of the enum that it's storing, but we would actually want to see the number, like the actual memory representation of this enum. To do that, we can look at the variable, but format it as a digit. So for example, if we look at the get variable as a digit, we see that it's equal to 0, and then delete would be 1. What else do we have? We have post, that's 2, and put, that's 3. So this is how enums are actually represented in memory. They are just a simple number. Okay, another interesting feature of the enums is that we can specify a value for the variance. So it's not necessary that the get is 0, like this enum might start with something else. So for example, here we might decide that we want post to be equal to 5. That means that get would still be 0, delete will be 1, but then post will be 5, and everything else will start incrementing from this 5. Let's actually see that in action. If we rebuild our project and run GDB again. Okay, if we put our breakpoint again and run. So now, we still have the same thing, but if we look at get, it is still 1. It is still 0, excuse me. Delete is still 1, but actually post will be 5 and put will be 6. So we can control what values the enums would have in memory. This can actually be quite useful. For example, later when we are implementing the status codes for our responses, we can use an enum, and the variant of the enum that is not found can have the value 404. Okay, let's leave this enum like this for now. So this is the simplest type of an enum, but enums are actually much more powerful. Rust's enums in their full glory are similar to the unions in C, but just on steroids. We can associate different types with every variant of an enum. For our method here, this is not very useful, but let's imagine that for the get, for example, we would also want to store the query string that we have received. So we can say that the get variant actually contains a string. And for the delete, we might know that when we receive a delete, we would want to delete a user from the database, let's say. So we want to associate some ID with the delete. So now, this is still a completely valid enum. All of these variants will contain no data, but these first two will contain some data, and the most powerful thing here is that they can contain different types of data. So if we come up here, now when we create the get variant, we can actually pass some string here. And this will work. And we can do the same for delete. We can pass some number. But all of the rest of the variants like will hold no data. Now how this would be represented in memory is every variant of this enum will take up enough space to hold the largest variant. This is a bit weird to wrap your head around. So the compiler does not know what variant an enum might have. Like the compiler only knows that this, for example, is a method, but it doesn't really know if it's going to be get or if it's going to be put. So for the method enum, the biggest possible case is if it's get that holds a string, because the string representation on the stack is bigger than just a number. So for every variant, it will allocate enough space to be able to hold the largest one. Okay, now let's delete the necessary code here. We don't need to store any values there, and we can delete this example. Now we have some decent representation of a request. One thing that we did not think about is what happens if the request did not contain a query string. What would we store here?